Bismillah. Hello and welcome to a new lesson. This is Dr. Gamal from your channel Think Math. In a previous video, we talked about the graphs of basic functions, and today we are going to talk about the transformation of curves. Understanding how curves change under different transformations will help you master algebra and calculus. This is a very fundamental concept in mathematics and helps you understand many functions and how to relate them and how to solve them. First, let's talk about the families of curves that we talked about in the previous video. We talked about the linear functions, which are represented by straight lines of the form f of x equals ax plus b. Quadratic functions, the general form of this equation is f of x equals ax squared plus bx plus c. And the cubic function, f of x equals ax cubed plus bx squared plus cx plus d. And the absolute value function, which are V-shaped graphs, where the general form is f of x equals a times the absolute value of x minus h plus k. The reciprocal functions, which have the shapes of hyperbolas, and they have the general form of a divided by x minus h plus k. Let's first talk about the basic quadratic function. So the simplest form of the quadratic function is f of x, y equals f of x, or y equals, or f of x equals x squared. So this is our parent function. Notice the blue parabola, and this is our starting point here. So notice when x equals 2, we get f of 2 equals 2 squared, which is equal to 4. The point 2 and 4 is marked with a green dot. This parabola opens upward with its vertex is at the origin, the point 0 and 0. Now let's apply our first transformation, which is the vertical translation. When we add a constant to our function, f of x plus 4, the entire curve shifts upward by 4. So y equals f of x plus a. So our a here is 4, so we shift the entire curve up by 4. Watch the green point at 2 and 4 move to the blue point at 2 and 8. Notice the x-coordinate stays the same, but the y-coordinate increases by exactly 4. The equation becomes f of x equals x squared plus 4. Okay, now what happens if we subtract f of x minus a? So when y equals f of x minus a, then we are making a vertical translation but downwards. So when we have f of x minus 4, or x squared minus 4, this is shifted downwards by 4 units. The point that was at 2 and 4 now moves to 2 and 0. The entire shape remains identical, only its position changes. Okay, now let's return to our original function and make a horizontal translation. This one surprises many students. So when we write y equals f of x minus a, so for example, f of x minus 2, or f of x equals x minus 2 all squared, the curve shifts 2 units to the right. We need the vertex to be at the point 2 and 0 instead of 0 and 0. So our point moves from 2 and 4 to 4 and 4. Now, if we want to shift it to the left, where we have f of x plus 2, or y equals x plus 2 all squared, and this shifts the parabola 2 units to the left. Now x equals negative 2 makes the expression 0. The point 2 and 4 moves to 0 and 4. Remember this rule when you are dealing with horizontal translation. Inside the function, signs appear reversed. Okay, now let's stretch the curve vertically. When we multiply by a constant greater than 1, like f of x equals 5x squared, the curve becomes narrower and steeper. Each y value gets multiplied by 5. So our point, which was at 2 and 4, becomes 2 and 20. So the y coordinate was multiplied by 5. It became 20 instead of 4. So it is 5 times higher now. The parabola hugs the y-axis more tightly. This is a vertical stretch. Okay, now for horizontal stretching, we have now y equals f of x divided by a. So x squared, so f of x equals x squared divided by 4. And this widens the parabola. So the curve spreads outward. The point at 2 and 4 moves to 4 and 4, okay? Because now we have moved right while keeping the y value the same. This seems backward at first, but think of it as needing larger values to reach the same y value. Now, if we looked at a different transformation, which is the reflection about the x-axis, so when we have y equals negative f of x, or f of x equals negative x squared, so f of 2 becomes negative of 2 squared, which is negative 4. So the curve now is reflected about the x-axis, and it now, the parabola opens downward instead of upward. And the negative sign in front of the function flips the graph vertically. Now we are going to deal with the reflection about the y-axis. To demonstrate this, since this is a symmetric function about the y-axis, it's an even function, we need to shift it horizontally first before we apply the reflection about the y-axis. If we have y equals f of negative x, first we have translated it horizontally, so we are dealing with f of x equals x minus 2 all squared. Now, if we take f of negative x, so it becomes negative x minus 2 all squared. For example, of f of negative 1 equals negative of negative 1, which is positive 1, minus 2. So it's negative 1 again. And then if we square it, we get 1. So look at the two blue points. They are symmetrical about the y-axis. And this is the reflection about the y-axis. Both of them, this is f of negative 1 and f of 1 lie at have the same y value. This is reflection about the y-axis. Okay. Now we start explaining the absolute value transformation. What happens in the absolute value transformation, we will show it now, but we first need to take a function with vertically translated. So we take the f of x minus 4. So we translate the function vertically downwards. So we have f of x equals x squared minus 4. Then f of 0, instead of being at 0, now it shifts 4 units downwards. So f of 0 equals 0 squared minus 4, or at negative 4. Okay, now if we apply the absolute value transformation, we take the absolute value of f of x. F of x minus 4, so x squared minus 4, if we take its absolute value, so instead of having negative 4, the absolute value transforms it to 4. So f of 0 becomes 4 instead of negative 4. This reflects any negative portions above the x-axis. Where the parabola dipped below 0, it now bounces up. The zeros at x equals plus and minus 2, so they remain because these are the points where the curve of the function meets the x-axis. But now the graph looks like two valley-shaped pieces joined at the x-axis. Now we are going to explain another type of absolute value transformation. This is when we apply the absolute value to the x, not to the whole function. But in order to do this, we need to take the horizontally shifted curve. So we take f of x minus a, or for example, f of x equals x minus 2 all squared. Now, if we apply it to f of negative 2, we have negative 2 minus 2 all squared, which is a negative 4 squared, which is equal to 16. But now if we apply the absolute value to the x, or to negative 2, so the f of absolute value of x, so f of x becomes absolute value of x minus 2 all squared. So for example, f of negative 2 equals absolute value of negative 2 minus 2, so it becomes 2 minus 2 all squared, so it's 0 squared, so it's equal to 0. Now, let's return to our original function, fy equals f of x, or f of x equals x squared. And for example, we have f of negative 2 equals negative 2 all squared, which is equal to 4. And let's apply multiple transformations to this. These multiple transformations are what we generally deal with in functions, in mathematical applications. So for example, if we have y equals a times f of x plus b, for example, f of x equals 3x squared plus 5, then f of negative 2 equals 3 times negative 2 squared plus 5, so it's 3 times 4, 12, plus 5 equals 17. So f of negative 2 shifted upwards by 5 and was stretched vertically by 3. Let's now look at another kind of multiple transformations. So if we have y equals f of ax plus b, for example, f of x equals 2x plus 2 all squared. This time, let's take an example at f of negative 2. f of negative 2 equals 2 times negative 2 plus 2 all squared. So it's negative 4 plus 2, which is negative 2, then all squared, so it becomes 4. This time the function was horizontally translated by 2 and horizontally stretched by 2. Okay, now let's talk about the reciprocal functions and the relation between the original function and its reciprocal transformation. So what happens when we have y equals 1 divided by f of x? For example, let's start by the basic reciprocal function that we have talked about in the previous video. So when y equals 1 over x, so when the function, let's see here, when y equals x, we have a straight line. So when f of x equals x, it is represented by a straight line passing through the origin. So when the function f of x equals x has a 0, the reciprocal function f of x equals 1 over x has a vertical asymptote. This is at x equals 0. Now let's look at the reciprocal of the quadratic function. When y equals 1 over f of x or y equals 1 over x squared. So when the function f of x equals x squared has a 0, the reciprocal function has a vertical asymptote. And this happens at x equals 0. Now we notice that the reciprocal of the quadratic function is represented by the green lines on the graph. Okay, now what happens when we have a translated reciprocal? Okay, so f of x equals 1 divided by x squared minus 1. This introduces two vertical asymptotes at x equals negative 1 and x equals 1. Because these two values, when x equals 1 and when x equals negative 1, are the zeros of this of the denominator, so that's why they give us two vertical asymptotes. Now let's take some examples about the transformation of graphs. So example 1, use the curve of the function f of x equals 1 over x to represent the function f of x equals 2x minus 1 divided by x minus 1. To solve this problem, we simplify f of x equals 2x minus 1 divided by x minus 1. Let's rewrite the numerator. So 2x minus 1 equals 2x minus 2 plus 1 divided by x minus 1. Or we can take factor the first two terms. 2 multiplied by x minus 1 plus 1 divided by x minus 1. And this is equal to 2 plus 1 divided by x minus 1. Okay, so this shows that f of x equals 2x minus 1 divided by x minus 1 is the curve of f of x equals 1 over x translated vertically by 2 and horizontally by negative 1. If we plot it, we see it as the red curve here that is a vertical translation by 2 and horizontal translation by negative 1 of the basic reciprocal function. Now the vertical asymptote moves from x equals 0 to x equals 1, and the horizontal asymptote moves from y equals 0 to y equals 2. Now let's take another example. Describe two transformations which transform the graph of y equals x squared to y equals 3x squared minus 12x plus 12. Okay, now let's take 3 as a common factor from the whole equation. So f of x equals 3 multiplied by x squared minus 4x plus 4, which is equal to 3 multiplied by x minus 2 all squared. This means that the curve of x squared is stretched vertically by 3, so the parabola becomes narrower, and it's horizontally translated by 2 to the right, so the vertex moves from 0 and 0 to 2 and 0. So watch the blue parent parabola stretch vertically and shift right to become the red parabola. In this transformation, the order doesn't matter for these transformations, and the result is the same regardless of which one you start with. The following example reads, what two transformations convert y equals x squared plus 6x minus 1 to y equals x squared? Okay, now we need to undo transformations. So first we complete the square on the left side. X squared plus 6x minus 1 equals x plus 3 all squared minus 10. So we can say that x squared plus 6x minus 1 can be transformed to y equals x squared by a vertical translation by 10 and a horizontal translation by 3. Okay, one more example is now sketch the graph of y equals 1 divided by 3x squared minus 12x plus 12. We can see that y equals 1 over 3x squared minus 12x plus 12 equals 1 divided by 3 times x minus 2 all squared. So this is the reciprocal of a stretched and shifted parabola that we have seen in the previous example. And the vertical asymptote is at x equals 2, where the denominator is equal to 0. So we can say that y equals 1 over 3x squared minus 12x plus 12 is the graph of y equals 1 over x squared transformed by a vertical stretch of 1 over 3 and the horizontal translation of negative 2. The transformed function is represented by the purple curve, while the green curve shows the graph of y equals 1 over x squared. Okay, so in this video we have explored the fundamental transformations, where we did the vertical and horizontal translations which shift the graph, vertical and horizontal stretch which change the shape's width, and reflections where we flip the graph, and we have absolute value transformations which reflect negative portions, and multiple transformations which combine to create complex curves. And these rules apply to all function families, whether it's quadratic, reciprocal, exponential, or trigonometric, and more. Thank you for watching, and if you have benefited from the video, please like and subscribe. And if you need personalized help in math, check the links in the description, and check our previous videos, which you will see in the playlist in the description of this video, and see you in upcoming lessons.